Hello, Mr. Betts here. Let's take a look at an example of an optimization problem. So we want to design an open box having a square base and a surface area of 108 square inches. What dimensions should the box have in order to produce a box with maximum volume? So first thing I'm going to do is try to figure out what's going on in the problem. I'm going to draw a picture. An open box is going to have a bottom but not a top. So we're going to have something that looks a little bit like this. You do not have to be artistic to be able to draw something like this. I will not grade artistic ability here, but the key here then is that it has a square base. So the bottom of it's going to be square. So I'm going to call the length of one side x, and then since it's square, the other side is going to be x. We don't know what the height is, so I'll call that h. And let's figure out what kind of restrictions we're going to have on x and h before we move on. So I know x can't, it actually can't be 0, because if x is 0, then we wouldn't have any surface area at all. X could be really small though. X could be like a half an inch or a quarter inch or even a 32nd of an inch. It would be if x is small, it would be a really skinny, tall box, but it is possible. So the values of x can approach 0, but they're never going to equal 0. There's also no biggest possible value for x, because let's just say x is 1,000,000, then the base is going to be have an area of 1,000,000,000,000, and so the height is going to have to be some fraction to make the height times 1,000,000,000,000 equal to 108. So the x could be really big. It can approach infinity, and if x is a really big number, then the height's going to be really small. There's going to be some sweet spot in the middle where we're going to get a really big volume. So if x is small, it's going to be skinny and tall, and it's going to have a small volume because it's really skinny. If x is really big, it's going to be really short and have a small volume because it's so short. So we want to figure out what dimensions are going to give us the biggest volume. And then with those restrictions on x, we're going to have similar restrictions on h. H could be really small when x is really big, or h could be really big when x is really small. So this is an example of one where we don't have endpoints. It's an open interval. So when we're justifying our answer later, we're not going to be able to use the candidates test because we don't have endpoints on this. So moving on to the second step, I want to write a function, and that function is going to represent what it is I'm trying to maximize. In this case, I'm trying to find the maximum volume. So I'm going to write an equation for the volume of this box. So the volume is going to be base times height times width. So it's going to be x squared times h. I do want that equation to be in terms of just one variable though. So I need some relationship here where I'm going to be able to get rid of either the x or the h from this equation. And that's going to come from the surface area here. So the surface area of this box, remember there's no top. So the surface area is going to be the area of the bottom plus the areas of all four sides. And each side is going to have an area of x times h, and there's 4 of those. So the total surface area of this box is going to be x squared plus 4xh, and we know that that surface area has to equal 108 for this box. I think the easiest variable to solve for, since there's an x squared and an x here, it's going to be easier to get h by itself. So let's do that. We get h equals 108 minus x squared over 4x. And that's going to equal, I'm going to simplify this and divide each term here. So 108 divided by 4 is 27. So we get 27 over x minus x over 4. So what I can do with this is I can replace the h in this equation, and since that's in terms of x, my volume formula is going to be entirely in terms of x. So let's go back to that and write it out. So we got volume equals x squared times 27 over x minus x over 4. Now, keep in mind, we're going to be doing some calculus on this later. So I'm going to distribute that x squared and just make this a little bit prettier. So we're going to get 27x minus x cubed over 4 for our volume. So depending on what x is, we can plug it into this equation and it's going to give us the volume. And we don't need to know what h is because we incorporated that in here. So the next thing I want to do is figure out where we could have a maximum volume. And that's going to occur at the critical values for this volume function. So I'm going to take the derivative. That's going to be 27 minus 3x squared over 4. And I want to set that equal to 0. So I want to know when is the derivative equal to 0 and when is the derivative undefined. Well, this derivative is never going to be undefined, but it is going to equal 0. So we're going to have, that's going to be 36. So x squared equals 36 and x equals positive or negative 6. Now, I did include both values of x here, but I think it should be pretty quickly obvious that x should not equal negative 6. This is one of the important reasons that we established the domain of x early on so that we know what values we can throw out pretty quickly. But it wouldn't make sense to say x is a negative value because x represents the length of the side of a box. So a length can't be negative. So we'll throw out our negative 6. And remember, the candidates test isn't going to work here. So we're going to have to rely on the first derivative test. And remember, the first derivative test only works for global extrema if there's only one sign change. So hopefully, if we make a sign chart for v prime, I'm going to start at 0. And it's going to go all the way up to infinity. So the values that I'm plugging in here are x values. And I'm going to put our critical value of 6 on here. So 6 is the only place that the derivative can change signs. So that's hopeful that we're only going to have one sign change and the first derivative test will work. So let's plug in a number between 0 and 6. I'm going to just choose 1, make it pretty easy. So we're plugging into the derivative because we're making a sign chart for the derivative. If we plug 1 in, we're going to have 27 minus 3/4, which is 26 and 1/4. The important thing is that it's positive. So v prime is going to be positive between 0 and 6. If we plug in a really big number, say a million, when we square the million, we're going to be subtracting a really big number. And so this is going to give us a negative. So what this tells me is that to the left of 6, as x increases, the volume increases because we have a positive derivative there. And then to the right of 6, the volume starts decreasing. So as x gets bigger, closer to 6, the volume's also getting bigger. And then once we hit 6, the volume starts getting smaller again. So at x equals 6, we're going to get that maximum volume. Okay, so using the first derivative test, we're going to say max volume, and this is not answering the question yet, but max volume at x equals 6 because v prime changes from positive to negative, and it's the only sign change. Okay, so I did the justification step already, but I didn't answer the question yet. So the question says, what dimensions should the box have in order to produce the maximum volume? So dimensions of the box, I'm gonna separate this, and I'm gonna say the base dimensions will be, so the base is x by x. Remember we said x is gonna be 6. I wanna include units, so 6 inches by 6 inches, and the height is going to be, so we need to figure out what the height is, and I'm going to plug the 6 into that equation right there to get the height. So we have 27 over 6, which is the same thing as 9 halves, minus 6 over 4, which is 3 halves. 9 halves minus 3 halves is 6 halves, which is 3. So the height is going to be 3 inches. So the dimensions that are going to give us the maximum volume for this box is going to be 6 by 6 base with a 3-inch height.